Lesson 3 is about Lewis structures, which are ways of drawing covalent compounds. So we're going to be talking primarily about non-metals only. And in class, we did a lab that talked about the solubility of covalent compounds in one another. Here we see that the blue dye was most soluble in water. Now, before we can do more in-depth chromatography, we really need to understand how to draw Lewis structures. Okay, so you got an idea about how to calculate the RF value from this. You saw that the blue dye was most soluble in the water. Now it's time to really learn how to draw them. So in this lesson, I'm going to do 5 examples along with some notes. I'm going to go really slow with them. These are basic examples. In class, we're going to do a ton more, and we're also going to learn about some of the properties. So we'll be talking about polarity and things like that. So here we go. We're going to start off with some basic notes. I want you guys to watch this video carefully. Take down every single thing in your notes. Okay. So before we start, we need to understand and revisit this idea of the valence electron. Okay, and the valence electron or electrons are electrons in the outer shield. Okay, what do I mean by that? So if we take oxygen, oxygen's electron configuration is 1s2. 2s2, 2p4, and here's the outer shield, that second shield, and there are 6 there. So for Lewis structures, those are the only electrons that we are actually concerned with. Shall we show them as dots? So 1 dot there, 2 dot, 3 dot, 4 dot. All of these are singular dots, and then we start pairing up. And these are called lone pair of electrons. And these are the bonding electrons, the ones that aren't happy. Now conversely, if we look at a noble gas like neon, 1s2, 2s2, 2p6, and we look at the last shield, we see 8. So if we do neons, this is called Hund's rule, giving them all singular dots first. Here you have 4 lone pairs of electrons. So you have no bonding electrons, which is why Regina George is always hanging out by herself at the table. And that gets us to something called the Octet Rule. If you notice, 4 lone pairs is 8 electrons. And that's how many valence electrons all atoms want. Okay? Atoms want 8 valence electrons. Now, hydrogen is an exception. It only wants 2. So let's go ahead and look at what this might look like when you're drawing some structures. So you're going to end up often with cases where water is either going to, or oxygen, is either going to have 2 bonds that way or 2 bonds this way. Well, it's important to remember that inside this covalent bond, this is the sharing of 2 electrons. So if I think about the octet rule, I have 1, 2, 3, 4. Well, I need 4 more. And those are going to be filled in as lone pairs, just like that. Here, 2, 4, 6, 8. If I had something like this with nitrogen, or even something like this with nitrogen, or even something like this with nitrogen, okay, which are the 3 cases of nitrogen that you'll see most often, I need to still satisfy the octet rule. So 2, 4, 6, I need to add 1 more lone pair. Now there are 8 there. 6 of them are tied up in the covalent bond, and 2 are not. Here again, 2, 4, 6, there it is, 8. 2, 4, 6, there it is, 8. Now there are 2 types of elements that primarily will have only 1 bond connected to them. Hydrogen and then the halogens. Let's look at chlorine. Now, hydrogen is fine the way it is. Remember, hydrogen only wants 2. It's trying to be like helium. So hydrogen's got its 2. The octet for hydrogen is really just 2. Chlorine's not. It's got its 2. So how many lone pairs do you think chlorine is going to need? It's going to need 3 lone pairs. Now it's got its 2 in that covalent bond, and then it's got the 6 remaining, giving it its octet. So what we're going to do is do some examples right now. But to start off, I'm going to give you the rules with the first example, and then we're going to have you press pause, try the others on your own to see if you got them right. So let's do this first one together. First one we're going to do is carbon dioxide. Okay. So the first thing you want to do when you're doing a Lewis structure is you want to draw the skeleton. Now normally the first element, or the one that occurs the least, is the central atom, and we're looking for symmetry. So that's another thing to think about. So there's the skeleton. The next thing we're going to do is we're going to add up all the octet electrons, okay? And we're going to subtract that from all the valence electrons. So oxygen, carbon, and oxygen all need 8 for their octet, so 8 times 3 is 24. Now let's subtract that from the valence electrons. Well, here's carbon, okay? Carbon has 4 valence electrons, and oxygen has 6. And this reminds me that a really easy way to get the valence electrons is just to get the column on the periodic table, okay, rather than doing the electron configuration each time. So carbon has 4, oxygen has 6, so 6 times 2 is 12, plus 4, that's 18. Not 16, sorry. Subtract that, we get 8. What is that 8? That is the number of electrons available for bonding. But remember, a covalent bond involves 2 electrons. So we divide that by 2, and this tells us that we have 4 bonds. So I'm going to put those in. 1 here, 1 here, 1 here, 1 here. All right. And the last thing I'm going to do is I'm going to check for my octet on each element. So I have O, 2 O's, and a C. So I'm going to check for my octet. So this first O, 2, 4, does not have its octet, so I got to add lone pairs, 6, 8. We're good. Other O, 2, 4, 6, 8, we're good there. And carbon, 2, 4, 6, 8, carbon's good to go. All right, so the Lewis structure for carbon dioxide looks like this, and it's actually a linear molecule. And we'll be going over the shapes in class next time. And they're also in your book starting on page 59. Let's do another example now. Now that you have some basic skills, I'm going to have you trying to do them on your own first. So try and do H2O the way I showed you. Now I know you know a way of doing it on your own. Try and do it the way that I showed you. This is a foolproof way of doing it that's going to allow us to do larger molecules in the future. Press pause. So let's go through and do it. Skeleton first. In this case, O is going to go in the middle. Hydrogen can't have more than 1 bond, so it's impossible for it to be in the middle. 2, we're going to get the octet electrons. Well, O has 8. Hydrogen only needs 2 for its octet. So we have 8, 10, 12 total electrons minus valence. Hydrogen has 1, 2, plus oxygen 6, that's 8, giving us a total of 4 electrons available for bonding. Those electrons are in a covalent bond, so we're going to divide by 2, and that's going to give us 2 bonds. There it is. Now what we're going to do, we have 2 H's and an O. We're going to check for octet. So H and H, both of those are satisfied because remember they only want 2. The oxygen, 2, 4, not satisfied, so we have to put lone pairs. And the way this actually looks, those lone pairs push on that bond and bend them, so this molecule is called bent. And that's water. Let's go ahead and try another one. I'd like you guys to, again, try it on your own, press pause, and then press play to see if you got it right. We're going to do SO2. Skeleton structure. S occurs the least. To make it symmetrical, I put it in the middle. Octet of electrons. Each of these needs 8, so that's 24. Valence electrons. These are both in the row that has 6 valence, so that's going to be 18, 6 times 3, leaving us a total of 6 electrons available to bond. but because those are in covalent bonds, we divide them by 2, and that's going to leave me with 3 bonds. 1, 2, 3. Perfect. You might end up with the bond on this side depending on what side you start on, and that's going to lead to something called resonance later. Okay, now for our octet, we got O's and S's. This first O has only 2, so I need to add 3 lone pairs to get from 2 to 4 to 6 to 8. Good there. Let's look at the other one. 2, 4. That has 2, so I just need to put 2 more lone pairs. And this sulfur, 2, 4, 6, needs 1 lone pair. Much like water, this molecule is also going to be bent. Again, don't worry about this. You might already know it. This lone pair here pushes on these bonds to bend it. Let's try another one. Let's do CH4. Like you do, press pause, try it, and then press play to see if you got it. So, skeleton structure. Total octet electrons, 8 here, 10, 12, 14, 16. Remember, hydrogen only needs 2. Valence electrons, we got carbon here with 4, 5, 6, 7, 8. Giving us a total of 8 electrons available for bonding. Those electrons are tied up in covalent bonds, so they're spread over 2. That gives us 4 bonds. And let's see if each element has its octet satisfied. Hydrogen only needs 2. 2, 2, 2, 2. So each hydrogen is good. And the carbon needs 8. 2, 4, 6, 8. Good to go. Now this molecule, it's tempting to draw it in a T like this, but it actually forms what's called a tetrahedral molecule, where you have this pyramid here at the bottom. This is actually sometimes drawn with a wedge, showing that it's coming out of the board, and this is sometimes drawn with a dash. But either way, this is called a tetrahedral molecule. Let's do another example. In this case, we are going to do an ion, SO4 2-. Now, when you see an ion, what this means is you have 2 extra valence electrons. So that's plus 2 electrons extra to give it that charge. So let's go through, and why don't you just do this one with me. We're going to set it up, our structure. S in the middle, O's on the outside, and you always put a polyatomic ion in brackets, and you put its charge up here at the top. 2, total octet electrons. Well, you have 5 electrons, all needing 8, total of 40. You have 5 electrons, all having 6 valence. That's 30 valence, but we have to add 2 more valence electrons, plus 2. So 40 minus 32 in this case is 8 electrons available to bond. But those 8 electrons are distributed over 2 places. That gives us 4 bonds. Now what we're going to do is check everything out. So we got 4 O's and an S. All of these O's need 3 more lone pairs. And if you're in a bind, sometimes you can just draw the lone pairs as lines. I don't mind you doing that. Now they all have it. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So, boo, 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 boo. And the S, 2, 4, 6, 8. Good there on the S. So this molecule, when you look at it, actually forms another tetrahedral. But you got to put that charge out there for the polyatomic ion, okay? Now, I'm going to leave you guys with a challenge problem to do right here. I want you to try and do NH4+. Press pause, and then press play to see if you got it right. So let's do this one. N, H, 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 2. Total octet of electrons. So hydrogen only needs 2. 2, 4, 6, 8 plus 8 is 16. Now, what do you think the positive means? That means minus 1 valence electron. So minus 1, and the total valence, 1 for the hydrogen, that's 4. 1, 2, 3, 4. Plus 5 for the nitrogen, because it's in the 1, 2, 3, 4, 5 column. So 5 plus 4 is 9. So 16 minus 8 is 8 electrons available to bond. 8 divided by 2 is 4 bonds. So this is the structure, tetrahedral. Okay. Now ask yourself, am I done? Is this complete? And the answer is no, because it's a polyatomic ion. So this is the ammonium molecule. I need to put it in brackets. Okay. So for your multiple choice question, now this is something I did not teach you in this video. I want to know what you think, because this is what we're going to do in class next time. Which of the following is a non-polar molecule that contains polar bonds? I want to see if you can figure this out. Okay? Press pause, try it out.